Hey guys, welcome back. Today we're actually doing a Western blot, and I just figured I would show you guys how to do it. And before I actually show you the actual procedure, I'm going to go ahead and go through the actual procedure with you, so that way you're not too terribly confused about it. What we use in Western blot are proteins, and what we do is we separate them by either charge and or the length of the protein, and the length is considered in kilodaltons. But what we're using, we're just going to be separating them out in length. And what we use for this is what is called a gel. And the gel can be made up of different things. Normally what I will use is a Tris HCl gel, but that doesn't really matter too much. What matters is the percent of it, because depending on if it's a 10% gel, which is the percentage versus how much water there is in it, or acrylamide, then that determines how quickly the proteins will be going. And this, I apologize about my drawing because I am terrible at it, but this is the gel, and what we do is we put the proteins into these little divots right here, which are considered as wells, and we will actually put a standard in there also that will have known protein lengths marked on it already in different colors, so that way we can compare it. And this is considered gel electrophoresis, and what will happen is we will run a current through it, and there's going to be a positive and a negative side. Sorry, I forgot to draw that. And what will happen is the proteins that we're using are going to be all negatively charged because we're using an SDS page, which SDS is a type of protein that will attach to proteins and make them be negatively charged. And so the positive will form more down here, and so the negative proteins will actually travel down the gel and will be separated out by the length of the protein. They'll stop at a certain place in the gel where it's their respective protein length. And over here, this is the actual Western blotting stage. What we're doing with this is going to be a transfer from the gel to a nitrocellulose membrane. Nitrocellulose membranes basically have a bunch of holes in them, very, very tiny, tiny holes that we can't even see, and proteins fit into them, and so it'll absorb any type of protein, so we actually have to be really careful when touching it, because proteins from our hands will actually stick on it too. And so what's happening here is this is the gel, and this is the membrane, and this is going to be the negative side, this is going to be the positive side. Because once again, the proteins are negatively charged thanks to the SDS, the proteins are going to be moved onto this direction, and the very first thing that's there is the membrane. The membrane will pick up the proteins, and then what we're going to have to do is then block the membrane so that way no more proteins can get on it, and so we don't have any cross-contamination. And then in the end, after doing staining with primary and secondary antibodies, which I'll explain a little bit later, we will have this membrane that will have the standard, which are known values, and then we'll have our protein, which what we're going to be using is called VEGF. And then say that protein is here, then we will know exactly what the kilodalton length of the protein is, and then we can compare it and make sure that it's the actual protein that we want, and from there we can just go ahead and see how much of the protein is actually in there. Alright, I'm going to go ahead and go a little bit deeper into the actual membrane and how we actually get to see where the proteins are. And with that, what we use are called antibodies. And most people know about antibodies, but they don't really know how they work, so I'm going to show you guys. Say this is an antibody, and these are proteins that it could attach to. Now, if you look at the tips of this, what it will have is a certain way that it is actually shaped, or in other reasons, it'll actually have different ends of proteins that attach to other proteins. And so, but just for a pictorial explanation, we're going to say that it just has a different shape. And so, as you can see, this is kind of triangular, and then we have VEGF is the protein that we're going to be looking at. And so that fits into that. So what you're going to have is those B film. And so what it's going to do is it's going to attach to that. And that is what we call our primary antibody. And so this will attach to the VEGF, which is going to be on a nitrocellulose membrane. So after that happens, what we're going to do is we're going to add a secondary antibody, which is going to attach somewhere onto this antibody. So I didn't really draw it in, but we'll go ahead and say that there's an area right there that the secondary antibody is specific for. So we're going to have an antibody that looks a little bit more that's going to attach to this. And so in the end, you're going to see it. Really sorry about this drawing. Look like that. This secondary antibody is going to have something else attached to it that normally what I use is horseradish peroxidase, that when you add an enzyme to that or some sort of substrate to it, it will give off a color. And so that way you can actually see where the protein is. And so we're going to have HRP, or horseradish peroxidase, that is also going to be hanging out with this guy. And then, like I said, we add a substrate that will actually cause it to have a colorimetric change, and then we'll be able to see it on this membrane. That is where I get where you can see this protein, and then the standards you can actually already see anyway. They already have a color to them.